Good afternoon, and thank you for joining us for today's Core Facility Seminar. I am Lisa Korpieski, the Director of Communications and Marketing at the Institute for Applied Life Sciences. These seminars are intended to provide awareness to the great work being done in the cores and to give you a chance to interact with both the facility team and your peers actively using these resources. Just a few quick housekeeping items. The seminar is being recorded. All replays of the seminars can be found on our website as well as the IELTS YouTube channel. We will save the Q&A till the end of the seminar. At the time, unmute yourself, please ask your question. I also want to remind everyone that you still have time to sign up to attend the Core Facility Showcase, the second annual Talk Tuesday, which will be held November 29th from 1 to 6 p.m. You can find more information and the link to sign up on the IELTS homepage, and I will put a link in the chat. Today, we are hosting Raman IR XRF Spectroscopy Core Facility with manager Zili Gao. Dr. Gao will tell us about the advanced spectroscopic analysis and other services available in his facility. Zili?
Yeah, thank you for the introduction and good afternoon, everyone. So in today's seminar, it will be two parts. The first part is I will introduce some of our lab research, mainly for the food analysis of Raman spectroscopy. And after that, I will introduce to you some of our other instruments and service we could provide to you and for the potential collaboration. So first, just want to make sure everybody can see my screen and can hear my voice.
Yep, you're fine.
Yeah. So first, let me introduce Raman spectroscopy. So Raman spectroscopy is a non-destructive chemical analysis technique. It can provide detailed chemical information such as phase, structure, crystallization, and molecular interaction. And this philosophy behind it is the interaction of light with a chemical bond from your material. So right here, I will show you a small project that to showcase how powerful and capable of Raman can do the chemical analysis. Okay. We have two nutraceutical compound here. One is lutein and one is zeaxanthin. So as you can see, they are isomers with very similar structure, and we want to see whether Raman could differentiate of these two isomers, and we want to see Raman could quantify the composition in the mixture form. And we also want to see whether Raman could characterize after heat treatment. And lastly, we want to see if Raman could mapping the distribution of a compound in its encapsulated form. So first, because these two compounds are lipophilic compound, we dissolve in oil at 1% concentration, and we can see the lower one is a spectrum from the oil itself. Once we add 1% of compound into the oil, either its combination or individual compound, we see that we can directly measure the sample from the oil, and the background of the oil is minimal. As you can see, those peaks when we have compound are very different from the oil pure background. Let me switch to another page. Okay, we also found that this compound, zeaxanthin, is more sensitive than the lutein itself, as indicated by the same amount of concentration with higher Raman intensity. So when we zoom in the spectrum, we found that some spectral shifts are different between these two compounds. And as you can see, the zeaxanthin is more on the right side of the rectangle, and the lutein is on the left side. And with this characteristic of these two compounds, we can okay, sorry, the computer is slow. So we can make a standard curve like this. And using this standard curve, we can predict the spectrum of this position, and the combination of these two compounds are the 82% versus 17%. And we also found that after heat treatment, the spectrum of lutein shift a little bit. And you can see here, there's a bump right here, and there's another bump right here. And after the heat, when we zoom in this spectrum, we can see a clear difference between the compound before or after heat treatment. And because of this compound is lipophilic compound and it's also nutraceutical compound, we want to improve its bioavailability. The most common way to improve its bioavailability is to make it into a emulsion, like oil in water emulsion. But how to see whether those compounds are successfully encapsulated in this droplet? So obviously, Raman can do it. We just simply draw a rectangle on above of this droplet, and we scan this area. And as you can see, when we choose the signature peak of the oil, we found that inside of this rectangle, the distribution of the oil is uniform. And when we choose the signature peak from the lutein itself, we found that the distribution of lutein is not uniform. It's in the center of this droplet. And this small project indicates that Raman is very powerful and capable to do the analysis. And this is a non-destructive method. You can measure your sample without breakdown, and the sample preparation procedure is quite straightforward and simple. But not every compound is Raman sensitive. Sometimes we need to use some other technology to improve its Raman signal, such as silver nanoparticle or gold nanoparticle. And this is so-called surface enhanced Raman spectroscopy and SERS here. So the principle behind it is when the sample close to the nanoparticle, such as silver or gold, when the laser hit the sample, and it will generate hotspots at the nanoparticle surface, and this hit hotspot will significantly enhance the Raman signal of the sample itself. So with this, we can improve the Raman signal of some chemical that is weak and to characterize its property. I will show one example. Oh, okay. Here's some commercial available Raman substrate, either solution-based or substrate-based. So those commercial available substrate are sometimes is very expensive and not flexible enough for fit your sample. And in our lab, we have like homemade substrate, which is easy to make at low cost, and we can overcome restraint of solid substrate, and we can expand the application significantly. So I will introduce two of our common used homemade substrate. First one is gold mirror. The principle of the gold mirror is we bought the commercial available nanoparticle, gold nanoparticle, and because the density of this gold is heavier than the water, it tends to at the bottom in the solution. So to stabilize this nanoparticle, they often coated with a silver citrate, and which is positive charge in the solution. So the nanoparticle could repel each other and to be stabilized in the solution. But once we add this nanoparticle in the organic solvent mixture, and the organic solvent mixture will remove this charge, then the gold will start to aggregate. And because of the density, the gold tend to settle at the bottom in this organic solver and to form a uniform monolayer gold mirror. And here, this is the picture of how mirror look like optically. And here is the ICM image. As you can see, this is a very condensed and uniform gold mirror layer. Here is one application of the gold mirror. So we have a pesticide here, and this pesticide has a nitrogen and carbon triple bond. This triple bond will have a signature peak at this position, and this pesticide itself is very Raman sensitive. But when we want to do the real application to measure its degradation or penetration on the plant, such as spinach leaf, there's no Raman signal from it. So to overcome this result, we will use gold mirror. And this is how the procedure works. So we have spinach and we have a few droplets of the pesticide. And after air dry, we drop a gold mirror on top of it. And as you can see, this is leaf under microscope without a gold mirror. And after we drop gold mirror on it, you can see a very shiny and uniform gold on top of that. So with this, we will be able to see the signal coming out once again. And using this signature peak, we'll be able to generate a very good linear standard curve for the further analysis. And besides mirror itself, we also generate some fiber-based substrate. And this is like commercial available stainless steel, and it's a fiber form. We coat gold on surface of this fiber, and you can use this fiber to detect the volatile compound in the heat space. This is very similar to the GC process. And here is one result. This is fiber without like spinach or the volatile compound, and the background is pretty minimal. And after we absorb the volatile compound on the fiber and detect on the Raman microscope, we can see there are some peaks pop out, which means this gold-coated fiber successfully absorbed the volatile compound, and those compounds can be detected by the Raman spectroscopy. And use this homemade fiber, we can detect the freshness of the vegetables. Okay, as you can see, when the storage time increased, we will find the peak at this region shift to the right side. And we also found that the peak at this region decreased. So besides the chemical itself, Raman can also for bacterial detection in food. And we have, okay, the principle behind is like this. We have a compound which is 3-MPBA, and we have a gold slide here. So the group right here on the 3-MPBA will coat or bond with gold on its surface. And the group right here could bind with the cell surface or the bacterial wall surface when under alkaline condition. And with this, we can optically see it under microscope. And since the bacterial is very close to the gold, and we can also measure this by Raman spectroscopy. Okay, and this is our previous data. We see that Raman could differentiate two different bacteria. One is E. coli, another one is Salmonella. And this is the research part. And this is our funding resources. So besides our research part, we also want to introduce some surveys and potential collaboration from our core facility. Our core facility equipped with 2 benchtop Raman, and both come with 2 lasers, and it equipped with confocal, which means they can measure your sample at certain specific depth. Besides these 2 benchtop equipment, we also have like portable Raman, which you can carry on site. We also have this handheld Raman, and this one can just simply hook on the computer, then you will be able to use that. And we also have FTIR, which is ATR based, and you can measure the spectrum with FTIR as well. Plus that, we also have X-ray and 3 types of different X-ray. Here's one example. We can measure the titanium dioxide with Epson 1. And with this instrument, we can mapping the element distribution. For example, I here have ample. I dropped some zinc side without angevin and another side with 1% of angevin, and we can see the zinc distribution on the ample surface. Without zinc side is more aggregate. With angevin, we can see the distribution of this zinc side is more uniform, which indicate that the angevin helps the zinc side distribution on the ample surface. And this is one example of FTIR. So you will be able to get the spectrum like this. And we also install some database. You can compare your spectrum into the database to find some potential match of your chemical. And this is our contact information. We are very happy to collaborate with both industry people and academia people to have a good collaboration. And thank you, Lisa.
Thank you, Zili. That was really informational. And I want to thank you all for coming. Your feedback on this seminar series is very important to us. If there are specific cores or technologies you would like for us to feature, whether they are part of the centralized core facilities or not, please let us know. You can contact Andrew or myself directly if you'd like. Stay warm and have a great afternoon.